Okay guys, now we're going to attack this workshop on multi-compartmental models. You should be very happy that in the past I had the students actually do the stripping of the curve, but you won't have to do that here, so you should be very happy. So I'm going to strip it for you and give you the data you need to make your calculation. So we know we have an 80 kilogram man who is given one dose of a trial drug, 750 milligram IV bolus. Concentrations were drawn as shown below. So here are the concentrations, and it was given as an IV bolus. So we didn't get a concentration at time 0, but a half hour in. And if we plot all of those numbers, first you have to take the natural log of them, or you can plot them on a log linear scale. But so taking all these numbers and plotting them on a log linear scale, we can see that this is the resulting graph. So the initial line looked like this, which was not straight. Therefore, we knew we had more than one compartment. So when we stripped it, this is what we got. The gray one is what we got for our slow compartment. So we followed along here for as long as we could, and then we get a slow compartment. And that point there is going to be our y-intercept, isn't it? Our natural log y-intercept, so we have to go and find out what the actual C2 is going to be, and the slope of this line will be K2, won't it? And then when you subtract out the remainder, you get these points here, which luckily make a straight line as well. So this is our first compartment, isn't it? And the slope of this line is our K1, and the y-intercept here is our C1. So you can see that here. Okay, so we've got all of these now. This is our stripped curve, and nicely I gave you the data, didn't I? So here's our fast compartment here. Our y-intercept is here, isn't it? Our C1 is 35.6. Can I read that? I don't know. Yeah, 35.6 is our initial intercept for our first compartment. Our y-intercept for our first compartment is 35.6. So I'm going to write that down. 35.6 milligrams per liter. I forgot to write milligrams per liter there, darn it. And times e to the negative k. So there is our K1, isn't it? So our K1 is 1.43 per hour. Because I should have written that in there too. And our second compartment, which is here, use a different color, which is here, our C2 is 15.64, and our K2 is 0.31 per hour. Okay, and this is in milligrams per liter, which I neglected to put on there. I'm sorry about that. So once we know those, which we're getting right from the equation that I gave you, which I had to actually figure out, then now I need to answer all these questions. So how many compartments are there? Well, there are 2 compartments. And please draw a picture of this model. Okay, so we gave it IV bolus into our first compartment, and then it moves at K12 over to our second compartment, and then K21 back. This is our bolus dose, which was like 750, was it? This is our microconstant K10. Oops. Now we need to figure out our half-life. How do we figure out half-life? Well, half-life is, and actually I don't think I went over this in the slides, which I should have, but half-life, so what K do we use to determine? Usually we can determine our half-life by 0.693 over K, right? But which K do we use? We have two Ks. Well, what do you think? What's going to be the rate limiting step to getting rid of the drug? The fast slope or the slow slope? It's a slow slope, right? So our slowest K is going to determine our half-life. So in this case, we want to use our K2. If we had 5 compartments, it would be the K5. If there's only one compartment, it's just our only K. So our K here, our slow K here is 0.31 per hour. So I'm going to go back down here. Oopsie. So we'll put in our K will be 0.31 per hour. So now we need to do our math. .693 divided by 0.31 gives us 2.23. I'm going to say 2.24. 2.24 hours. So time to steady state is just going to be 5 times that, which is 11.2 hours. What's our VC? Why can't I? Our VC, if you remember from the slides, you can also get out the equation sheet that I am going to be giving you for your test, which may be helpful. But VC is always the dose over your initial concentration, which in this case is going to be your C1 plus C2. Let me see if I think I wrote this down somewhere. Hang on, if I can find that little piece of paper. Okay. Our C1 I think is 35.6 and our C2 is 15.64. So we add those, and I think our dose was it 750 milligrams? So 35.6 plus 15.64. Okay, I got 50.24 milligrams per liter. So those milligrams will cancel and we have liters, which makes sense, right? So 750 divided by 50.24 is going to be 14.9. So this is 14.9 liters, right? What about V zeta? So I'm going to have to look up and see what V zeta, our equation for V zeta is, I think, K2, I don't remember. gonna have to go get. So basically, all you do is continue. I don't think you need me to show you how to plug and chug. V zeta, VSS, area under the curve. Area under the curve is C1 over K1 plus C2 over K2. That's easy enough. I know that one by heart. And then clearance is just area under the curve. Dose divided by area under the curve. You can do that one easily. And then, oopsie. The rest of these, the micro constants, you can figure all this stuff out just by following along with that equation sheet, and it's real simple. I will post the key, but I don't think it makes sense for you to watch me look up these equations and then do the math. I think you guys can do it. If you need help, let me know, but it's pretty straightforward. And then for your homework, it's just another one of these problems that I want you to practice doing on your own, so that you can answer these questions on the quiz properly. All right, awesome. Thank you so much.